maybe.
Alex wanted to do the fourth root of x, but we convinced her not to.
Well, it is funny because one of the, I think it was Marvin, did the cube root,
Nice.
and was, because he was determined to try and do number 2, but solve for y, but the parameterization's awful.
I believe it.
And so when they integrated, but like this one's nice, right? T comma t. And so it works out pretty nicely. And Alex was close on the t cubed comma t. No, which one was it? Yeah, you went along y equals t cubed as an example and almost got that. So yeah, what's going on here, guys? What's going on with this group work? That's what the story is today. We have something here called independence of path. It doesn't matter if I go along y equals x squared. Preston, you want to pass those back to those two? Or y equals x cubed, or we tried y equals x, right? What we're discovering here is a special phenomena called independence of path. And so this is kind of where I want to head now.
That's still in the first section.
And so again, we just did line integrals, and next time we're doing Green's theorem. Today, oh, okay, well, the title of the section for you guys, it's called Conservative Vector Fields. Now, we haven't said what that is yet, exactly, but it's related to this idea of independence of path. Okay? So, you guys computed the work, right? And you got the work is 3 over and over again. Right? So it's 3, but we had independent of the path chosen. Right? So we understand that the work in general, we said this at the beginning of class, is you're going to move along a curve, and you're going to integrate f, where f is the force field, dot t, where that's the unit tangent vector, and then ds, right? That was the game. So I guess, there's a few ideas going on here. And so I'm going to give you guys a theorem. And this theorem that we can prove will kind of explain what's going on behind the scenes here, at least a little bit. So here I go. Let C be a smooth curve. What do I mean by smooth? No cusps is a nice way to say it. The derivative exists, right? Parameterized by, we've been using R, so let's stick with R of t, and let's say that I want t to go between A and B. So for you guys, I think most of the time you had t going between 0 and 1, right, in the examples I saw? So all of those examples then would take you from 0, 0 to 1, 1. So that's one of the reasons I picked the point 1, 1 as our endpoint, right? Okay. And then, so here's, I guess here's the theorem. If phi, have we used that phi before?
Yeah.
For an angle, right? Well, this is a completely different phi. But your book uses phi. I was going to use little f. But your book uses phi, so I'm going to stick with it. So if phi is a continuously differentiable function on C, on the curve. So phi is something I can compute on that curve, and it's continuously differentiable. Then, and here's the theorem, I'll write it in black or something. Yeah. The line integral over C of, do you guys know this symbol? The gradient, yes. We're going to take the gradient of phi dot, and then I'm going to write dr Does that make sense to you guys? Maybe, we'll see. Equals f of r of b minus f of r of a. That's the theorem. I was trying to think, why is it not in your book? Well, maybe they didn't like this notation. Dotting the gradient with the differential of r. All right, but it still works, and I think you'll like seeing this. So I'm going to prove this theorem for you, and then I'm going to try and explain what's really going on in the book. So here's our proof. When I write this initial side down, so I have, let's see, this line integral C of the gradient of phi dot with the differential of r. Okay. Do you guys know what I mean by the differential of r?
Is the differential of r part of the integral?
Well, what's r? Let's go with that first. R is what?
Position vector.
Yeah. So how many dimensions do you guys want? Let's say 3. X of t, y of t, z of t, is that okay? Something like that? Because that makes it a function of t then, right? So if I'm in the world of 3D, oh, what's the gradient of phi? Let me ask that. You guys know what that is, right?
Yeah, it's like, well,
What kind of
are
derivatives?
we
What kind of derivatives do we need?
partial?
We need partial derivatives, right? So this gradient of phi, let me write that down. Gradient of phi, I guess, is, well, they're partial derivatives. So like the first coordinate would be partial of x with respect to t, et cetera, right? So if you believe that, then I think you'll be okay with me writing this first step of the proof. It's the integral of, bless you,
Thank you.
d phi, partial of phi with respect to x, dx, plus partial of phi with respect to y, dy, plus partial of phi with respect to z, dz. Yes? That okay? So now as my next step, I'm going to turn this into, well, okay, I'm going to take everything I just wrote and I'm going to play around with differentials. So I'd like to turn this into a dt problem. And so my next step, I will write d phi dx times dx dt plus d phi dy, and the d phi dy, those are curly, times dy dt plus d phi dz times dz dt. Can I do that? Well, that's one of the beautiful things about Leibniz notation, is that as long as you have regular old Calc 1 derivatives, You can kind of treat these things like fractions, the little differentials. And so that's what I'm doing, right? I'm multiplying top and bottom by dt. Yeah, I guess so. But now what is this? So here's the big step. This is the integral from a to b. If I'm moving along the curve of what? Of the derivative d dt of, so I claim that that thing in parentheses is something you've seen before. And you saw it a few chapters ago, not last chapter, but I guess 2 chapters ago, we studied the Calc 3 version of the chain rule. That's right. And when do you apply the chain rule? You apply the chain rule when you have a composition of functions, right? And I claim that all this is a composition of phi with what? With r. Do you see it? I mean, if you were to apply the chain rule 2 chapters ago to this, that's what you would have written down. The dt's out there still. Are you with me? Okay, well, I would really like to take the integral of the derivative. Wait a minute. We're in the Calc 1 world. By the fundamental theorem of calculus, I know how to do this. Right? Isn't that what the fundamental theorem says? It says you can take the integral of the derivative. What do? They kind of cancel each other. And so, I don't know if it depends which book you guys learned part 1 or part 2 out of. But the big theorem says we know how to compute this. Remember big F of B minus big F of A? That's what we're doing, right? Well, what's big F? Big F is going to be phi of R, right? So I have phi, oh, I stated this wrong. Sorry, guys. Remember I said, yeah, that's what I meant to see. Phi of R of B minus what? Yeah, there was no F. There was a phi. Why your book uses phi, I'm not exactly sure. Minus phi. Do they do this in physics, maybe? Maybe. I don't know. You haven't seen phi?
I'm in physics too, and we haven't. I don't think we've seen phi ever.
Okay. So we've seen phi used as an angle, which I know it is used at. Spherical coordinates, that phi is used. And now we're seeing phi. Well, what is phi? Phi is oh, wait a minute. No, Paul, you screwed up. Yeah, I used the phi in the wrong place. Yeah, so we're going to call phi here. This is what the book calls a potential function. A potential function. Okay? So I can give you a definition now, which should be nice. And what's the definition going to be? We need to talk about what a conservative vector field is. See, I guess what this theorem shows you is hey guys, when we computed work, right? That's the work integral, right? That's a lot like this. One of the big differences is that we have a gradient of phi, right? So we want my vector field F to be the gradient of some other function phi. That's what we're going to call the potential function. So Conservative vector fields are when this happens. Let me write it down explicitly, okay? So we say F is a conservative vector field if F is the gradient of what is called a potential function. And again, your book uses phi. Right? So again, F equals the gradient of phi. And this is nice. It is nice when this happens. What's nice about it? Well, for example, line integrals are easier because we will have, and again, the idea that we just came across in this group work was independence of what? Independence of path. So those are the main ideas that I want to get across today, I think. Now, have you guys talked about conservative vector fields in physics?
No.
No? Okay. Well, they will talk about those. They will talk about gravity being a conservative vector field, and I think that may be proven in the book. If not, maybe I should do that now. Yeah, that'd be a good one to do. All right, we'll do that. We'll do that as an example in just a second. But what I will, because I just like to translate for the people taking physics. There's always a number of you guys. So when we say conservative, you probably have heard this one in the physics classroom. They'll tell you the sum of, you guys were talking about potential energy, right? And kinetic energy is what? Mechanical. Is that what they call it?
They're
So I guess I'm not familiar with the
conservative force. We've heard of conservative forces.
conservative. Yeah. The point is that potential energy plus kinetic energy is constant. Like, I remember learning this much, right? So when I drop my pen, right, as soon as I let go, I gain kinetic energy, but I just lost some potential energy, right? And so if you believe that energy is conserved, okay, this is a conservative vector field situation. Again, I'm out of my league. I really shouldn't. I'm about to say things wrong if I continue. But I at least can say that much, that's related here. You know, how do you get potential energy? Well, let me just move on. I mean, back to the theorem we just proved. Maybe I'll say one more thing about that physics-wise. What is this really saying? Is this telling us that work is a decrease in potential energy? I'm gonna lose some potential energy when I move from A to B. That's interesting. All right. Well, like I said, I should stick to the math. All right. So let's do this. Let's talk about gravity, right? So here we go. So here's a question: is gravity a conservative vector field? Now, did I do gravity with you guys? I think so. I think we did this. We wrote down F. Yeah, we did this before your last exam. We said F of x, y, z could be thought of as negative, and then I used the gravitational constant, and I had an m for a mass. You guys remember this? Yeah, we do. No, we don't. Do you remember what exponent I had down here? With this x squared plus y squared plus z squared to the 3/2 power. You're really close. And then the x, y, z was right here, right? So that's my vector field for gravity, right? So the question I guess I'm going to ask is this the gradient of some other function phi? That's the question I'm asking. Okay. Well, if it were, suppose I have fx. Let's see. Yeah, I'm going to pause for a second here and think. Oh, for one thing, good thing, we didn't take our break yet. Is gravity the gradient of some function? So guys, I don't want to look at fx right now, although we might eventually. What I want to look at is, suppose it is conservative. My question is, what would phi x look like? That's my question. What would phi x look like? I'm saying this is, well, what do you mean integrated? With respect to what? This is a complicated thing we have here, right? It's a vector field, right? So it's a function of 3 variables, and in any particular x, y, z, I can give you a vector, right? This will be a scalar in front of a vector. That's why I wrote it that way. Now, by the way, here's one thing I could do. This is a big scalar, right? Couldn't I distribute it in, kind of? Right? And so you would see the x-coordinate, the y-coordinate, and the z-coordinate. And what I'm saying is this. If f is the gradient of phi, then what does this say? This says phi x. What does that mean? Another way to write it? Partial of phi with respect to x, right? That's another way to write it. So these are equal, right? The point is, if f is conservative, if gravity is conservative, then phi x, I claim, should look like this. Let's see if you agree with me. Negative g m x over x squared plus y squared plus z squared to the 3/2 power, right? Why is that? Because the partial means we're only looking at the x-coordinate, right? And if I take, guys, what's the gradient look like? Isn't the gradient the vector formed by these partial derivatives? And so what I'm saying is, the x-coordinate of this vector, which is that, would be d phi dx. If this thing is conservative. And so now I'm going to take Kathy's idea and I'm going to say, can we do this? Can we integrate with respect to x? Can we integrate this messy thing with respect to x? I think we can. Right? How would you do it? Well, if you integrated with respect to x, what I claim is we would end up with phi. Right? Because if this is partial of phi with respect to x, and if I integrate it with respect to x, I should get phi. I should get the potential function. Do you guys know how to integrate this thing? What kind of tricks am I going to use here?
Well, we'll just integrate with respect to x.
That's what we're doing.
U sub on the-
I agree. Let's let u equal, what? I guess this whole thing, right? X squared plus y squared plus z squared, right? And if I do that, then du would equal what? 2x dx, that's right. And so when I say I'm going to integrate this thing with respect to x, okay, couple things. First of all, negative gm, that's all a constant. Let's pull that out front, right? Negative gm, right? And then I'm going to divide by 2. Do you know why? We need the 2x dx. I have the x, I'm integrating dx, but I need the 2. And when I do that, then I claim what happens is I have a perfect u substitution. I get u to what power? Negative 3 halves du. So this works really, really well in this case. All right? So then when we integrate, let's see, we have negative gm over 2 times what? Well, it's going to be u to the negative 1/2, right? So what do I have to put out front? I agree, negative 2. So the 2's cancel, the negatives cancel. So this works out really nicely. What do we get? We get that the potential function would be gm over, because you see why I'm doing divided by? So the 2's cancel, the negatives cancel. This is u to the negative 1/2, so I'm just going to write it as over the square root of u, which is x squared plus y squared plus z squared, right? Are you guys with me on that so far? Cool. Oops. Plus, yeah, remember old plus c? All right. Well, our book is not going to write plus c for this kind of situation. And the reason is, it's not just a constant. It could be a function of y or z, or both, and I would be treating it as a constant. Does that make sense? So you could almost write plus k of y comma z. Let me see what your book will write, so I'll do the same thing they do. When they do a potential function, the constant, yeah, they'll write c or d. All right. So I'm going to say plus, c is good because it's kind of like constant, a constant of y and z, right? But that's the point. This would be the potential function. Okay. Now, if you believe me that actually this kind of goes away for some reason later, then we actually will see that yes, gravity is a conservative vector field. I guess I could show you the rest of the process in a moment. I think I want to go back to an easier example, though, like I said, maybe lower dimensions. So I guess my question is, should I go there? Yeah, let's go to the group work. Here we go. Back to the group work for a moment. And I guess it didn't ask you to do this on the group work, so I'll do it right in the notebooks. Back to the group work. Is the f there? And what did f equal? I guess it was, correct me if I'm wrong here, y squared plus 2x plus 4, right? That was the I component. And then you had 2xy plus 4y minus 5. Was that it? This is just two dimensions. So is this function conservative? Okay. Again, what does that mean? Is it true that f is the gradient of phi for some phi? All right, so how would this work? Well, if this is true, we need the gradient of phi to equal this, right? So we need basically two things. We need phi x to be y squared plus 2x plus 4, and we need phi y to be what? Exactly, the other side. So we need those things. So now what's the process? Same idea. Let's take this and let's integrate dx. And then what we'll have, guys, is we'll have phi. Phi will be a function of x and y. What would it equal? Well, xy squared, good, plus x squared, that's an easy one, plus 4x, and then plus, and again, this is where I decide what I want to write. Yeah, I want to see what your book writes with two dimensions. Do they write C or D? Yeah, they write C. So C of y, right? C of y. So now, I think this is kind of cool. Next step, let's do this. Let's take d dy, well, these would be partials, of phi. Let's take the partial with respect to y. Okay. That'll give me phi y. I get phi y is equal to, well, this would be 2xy, right? Plus 0 plus 0. There's no y's in there anywhere. Plus, and this would be c prime of y. You guys with me so far? Now, if you look at what I have two different expressions for phi y, right? Here and here. So what do I learn from those? Well, I could see that 2xy is in both of them, right? So now I go back here and I say, well, what else has to be true? That's right. If C prime y equals 4y minus 5, you can compute what Cy is, right? How? With respect to y. So C of y must equal, it would be 2y squared minus 5y, right?
Plus some constant.
Well, I guess plus a constant, right? Yeah. So the final answer, then, I guess, is it true that f is the gradient function for some phi? I guess the answer is yes. And the proof would be this. We would say, well, phi is equal to what? That's what we had up above, right? Not in the rectangle, but here. Phi is equal to xy squared plus x squared plus 4x, and then where it says C of y, what would I write? 2y squared minus 5y. And guys, it doesn't matter what constant I pick. Any constant I pick, this would be a potential function for the force field. So I will just use this with k equals 0 at that point. All right, so there's my phi. And how do we check? Well, to check, we can compute gradient of phi. Let's do that. This is good. We're reviewing all the stuff from 2 chapters ago, right? So gradient phi, it's a vector, right? So what would it be? Well, first I take the partial with respect to x, and what do I get? Y squared plus 2x plus 4. Isn't that what I had? Yeah. See, that's the first piece. See it? And then, of course, the other part you can get very quickly would be 2xy plus 4y minus 5. It had to check. That's how I got it, right? I just went backwards. So this is the process known as finding a potential function, okay? And so I demonstrated it for gravity in 3 dimensions, at least part of it. We didn't quite finish this last piece here. I guess I should really do, and maybe I will in a moment. One of the reasons I wanted to move on, though, is I thought I probably should show you an example of a vector field that's not conservative, right? And it's good to see both. So here's an exercise for you guys to try, and maybe I'll think about the gravity one while I do that. So here's the exercise, and I think I'll turn you loose for maybe 5 minutes tops on this. The vector field f of xy, we'll just do 2 dimensions. If I give you this one, 3y and negative 2x, this is not conservative. And I'd like you to find out why. And so what I suggest you do is try to go through the process we just did and see what breaks down, and maybe that'll be instructive, all right? You can work with someone. You guys are already working in groups anyways, so I'll pause for a few minutes here, and then we'll talk in 5 minutes or less. The process would be what? We're going to find phi. So what do? We would first say phi x. So suppose phi exists. Now it doesn't. It's not conservative, but suppose phi exists. That would mean that phi x would have to equal what? 3y. It would also mean that phi y has to equal negative 2x. But what people usually do is they just start with one of them. And if you integrate with respect to x, you get phi. And phi would be 3xy, right?
Well, isn't it 3xy plus some?
Plus some constant of y, right? Okay. But that's not true. Because now, well, what'd you guys do next?
And then I did, took it from y
Uh-huh.
and did negative 2.
S-
And then becomes negative equals negative 2xy plus
Y-
c of x.
Right, so some people will do this, they'll say, let's integrate this dy. But what I suggested the first time was, once you have phi, let's compute phi y this way. How? How do you get from phi to phi y? Derivative with respect to y. So we get 3x plus c prime of y. Now, we have 3x plus c prime of y, and that has to equal negative 2x. Not going to happen, guys. Because this is just a function of y. That's not going to happen. If you go the way Matthew was saying, what'd you get? You must have gotten negative 2xy plus some function of x, right?
Yeah, and then I combine the
And you say, are these the same? And the answer is no. They can't be the same. Right? You guys with me? Now, when Ryan did this, he followed a test from the book, okay, which is a really nice tool to have. It's kind of a quick way of testing whether or not you have a conservative vector field without having to go through the calculation, okay? And so here's the idea behind his test. Now let me write the test down and then show that, right? So, I mean, the idea, first of all, well, I'll write down the test and I'll show you the idea in the book. I think it's really cool. The test is that we will say that f is conservative if and only if and only if what? Take the partial of, let me write it down right. So I guess the problem is that I didn't tell you how many dimensions I'm in. Let's say we're in 2 dimensions. F of xy is conservative if and only if what? The partial of f Okay, so instead of writing it this way, that's my problem, is writing it that way. It's not okay. Try again. The test is for a vector field, right? Now a vector field has f, g, h, right? As its one last try.
For this problem, we just use this small.
Yeah, so for our problem, we're just going to do f of xy, let's say. So remember, the way a vector field works is you spit out, let's call it little f of xy and little g of xy. Let's write it that way. Okay. So if you have this, if we have this, yeah, so I'm basically reproducing a smaller version of this theorem. Then we can say f is conservative if and only if. Okay, so again, the implication works both ways here. And now you have to look at these little functions in here and take their partial derivatives. dg dx has to be the same as df dy, and these are partial derivatives, right? That's interesting though. It's the partial of the y coordinate with respect to the x coordinate and partial of the x coordinate with respect to y. Now, why is this true? Because, I kind of like the book's explanation up above here. You see these things here? Here, let me zoom in on that. There they are. phi xy equals phi yx. We learned that 2 chapters ago. We said, hey, when you take partial derivatives, you'll notice that you're getting the same values for fxy and fyx. That always happens, right? As long as your function is nice enough. And phi is going to be, we said, a continuously differentiable function. So these are going to be true. If phi xy is the same as phi yx, that's exactly what this would say. Because phi is kind of, right? These are the second derivatives of phi, you could argue. That's what's going on there. But anyways, when Ryan did ours, what was the function we said is not conservative? We said f of xy is
3y negative 2x.
yeah 3y and negative 2x, and so Ryan was doing this. He says, well, I'll do dg dx. That's this thing, right? So he got negative 2. And then when he had to do df dy, and he looked at that, he got positive 3. He said they're not equal. Oh, not conservative. Okay. Whereas, what about the group work? The group work, our function was, let's see. On the group work, we had y squared plus 2x plus 4. And of course, there goes my signal. But on the group work, we had y squared plus 2x plus 4. And then we had 2xy plus 4y minus 5. So what you might do when you guys are doing homework and you're trying to say, hey, is it conservative or not? Do the test. What are you going to do? Well, we'll take this and we'll take the partial with respect to x of this thing. And what would you get? 2y. And then the other one, we'll take the partial with respect to y, 2y. Okay? That's kind of your first step. Check and make sure it's conservative. Now that it is, then you can go through the steps of how to find it, which I already showed you guys. Does this make sense to you guys? Good. We've covered a lot, which is good. I mean, we're at 11:50, so I guess I'm out of time. But I think you guys should be good for the rest of it. We showed how to find potential functions, fundamental theorem. We didn't talk yet about closed curves. We'll talk about that next time. That's going to be important when we talk about Green's theorem. But nice work today, guys. Nice job on the group work and everything else.